Hello, everyone. This is the Healthy Planet Action Coalition, and we were very pleased to host Clive Elsworth and Franz Oeste, who are both very active members of our group and also leaders in the development of potential tropospheric aerosols that may serve to, for example, replace this sulfate aerosols in the high seas or per our paper on to the International Maritime Organization to that effect, and they can speak more about that if they wish to. But I know that they're both engineers and they've been working on this for many years, and I'm very happy that they have agreed to come and enlighten us about what they're doing and how they hope it will work, and then of course, as always, hopefully we will have a robust and interesting discussion after their presentation. So without further ado, I don't know, Clive and France would, yeah, please feel free to introduce yourselves some more if, because uh, I really don't know a great deal about your backgrounds other than that you're both, you have a long history in engineering of different sorts. And I know that France has in particular written and both many papers on iron salt aerosols and other things that directly relate to this. But I'll stop and let you guys take over.
Okay, thank you, Ron. Franz, would you like to introduce yourself first?
Okay. I'm chemical engineer and worked on the IS iron salt aerosol project, and now found a better way to do this, but not say better, say some more sorry,
what do you mean?
For that?
Not better, but more effective.
Cheaper, more effective and cheaper and more multiplied. Iron salt aerosol only makes mainly makes the methane depletion, maybe a little bit of ocean
fertilization,
and but what we now are doing is it makes the albedo, increases the albedo, and helps depletes methane, and is very much cheaper than the old ISA.
Yeah. Okay.
We think.
The iron salt aerosol.
Yes.
Yeah. Okay. All right. Thank you very much, Franz. I mean, you actually pioneered. You actually predicted that iron salt aerosol.
Excuse my bad English.
No. It's okay, Franz. You've been
yes.
the pioneer of all this, and never stopping to look for better ways, and understanding the natural chemistry that we can to see if it could be mimicked. So if we could use that natural chemistry, which is very low concentrations. Okay, thank you, Franz. I've try and be short about this. Neither of us have a university affiliations. Franz is retired. We'll say a little bit more at the end. I teach data analysis for a living, but I got interested in climate change, and to cut a very long story short, when I realized carbon pricing wasn't really going to happen in time anywhere in time, I was amazed when I saw Franz's paper from 2017 explaining iron salt aerosol. And then I offered to help Franz with writing, and he accepted, and that was in 2019. And so we've been working together since then. And it's been a hell of a learning journey for me to learn about chemistry of the ocean, and this is more about atmospheric chemistry. So okay, so I've been working on some slides, so let's get these slides going. Now, firstly, we want to call it natural tropospheric aerosol processes. Let's not talk about too much about naming right now. Okay, and then just for this evening, please, I teach for a living, so I do a lot of this, teaching other things, and I ask people to basically speak up, just interrupt. Obviously, if you can't hear or see or something, but also if you don't understand, I don't mind you saying just that didn't understand something I'm saying. I'd like this to be an educational presentation. So, okay. But on everything else, I'm sure many people will have all kinds of comments. I'm keen to hear that, and to be like a proper scientist, take criticism. We want to hear why, if anyone thinks this cannot work, we'd like to hear that. Okay, so I'm going to try and get it done within 30 minutes or less. Okay, some preliminary slides, which pretty much everybody knows this stuff. So let's go through this quickly. Jim Hansen said the effects of climate change will be delayed and then undergo amplifying feedback. So that future is here now. In the coming decades, we can expect climate tipping points. And I'm kind of shamelessly quoting Alan Gadian, who has been saying water vapor. He's very worried about water vapor in the coming decades, exceeding the warming of greenhouse gases, because it's a self-reinforcing feedback. The warmer it gets, the more water vapor gets into the air, and that is itself a greenhouse gas, and it's going to more and more render hot places unlivable. So I do wonder if most people just don't get it about climate change. It's just going to keep getting worse and worse and worse with no end in sight. And so, once again, Alan said much worse in about 5 years' time. Even in 2018, several power stations had to be closed in France because it was too hot for them to operate safely. I see already the price of coffee has gone up, not just because more people want to enjoy drinking coffee like we all, Western lifestyle, but also because crop failures in Vietnam and other places. So we know this is all going on, ecosystem destruction and worse weather and so on. And so we're very interested in the cooling power of aerosols. Obviously, it's not a complete solution, but it's the kind of tourniquet we talk about to help keep the patient alive while they recover from their disease. And so clouds are an example of aerosols. Cloud droplets are suspended in the air. They reflect away around about 22% of the of the sun's energy. That's a lot. They also trap heat, but low altitude clouds have an overall cooling effect, especially stratocumulus are of particular interest by meteorologists. There have, of course, been many studies on marine cloud brightening, which we're all trying to learn from. And I noticed them saying that the net cooling is about 20 watts per meter squared on average. I know that one person, Paul Stansel, we've been having a conversation about that. So, and he's a physicist. So keen to continue these discussions. Another thing that Alan
does Paul think it's higher or lower?
What's that, Brian?
Does Paul think it's higher or lower?
He thinks they cool by a higher amount, by about more like 47 watts per square meter.
Sounds good.
Yeah. So this would be a good thing for us to discuss later on, or in all our many meetings we have. So again, Alan said, and I asked him if I could quote him on this, and he said, as long as I say it like this: taken to extreme, marine cloud brightening could cause another ice age. So this is worthy of note. Okay, so I thought I'd just quickly throw this in. I have this printed and it's on my office walls. I look at it every day. to try and understand how that heat comes in and leaves the Earth every day. A huge amount of energy comes in. I mean, an eye-watering amount of energy comes into the Earth every day, but it leaves, you know, fairly immediately. You know, it's always cooling as well as heating. I found it rather interesting that when you add these numbers up, if you add up 100 watts per square meter, so this is scientists measure heating influences and cooling influences in terms of watts per meter squared. 340 watts per meter squared. If you imagine a 100-watt light standing under, well, the old incandescent light bulbs. If you stood under a 100-watt light bulb, you'd certainly feel the heat of it. So every square meter, we have 340 watts of heat energy coming in from the sun, and 100 of that gets immediately reflected back out to space, and the rest is thermal, so infrared. Of course, the Earth doesn't touch anything, so it can only gain and lose heat by radiation. It's interesting, if you add these numbers up, the difference is, so you get 339 plus 100, so a difference of 1. So that's the energy imbalance. It says it down here, 0.7 or 0.5 to 0.9. Okay, so that's the energy coming in. So that's where we get the 22% cloud reflectivity. If you take this 25 off, you get 75. Yep.
Could I just note there, in James Hansen's recent papers, he said that this 0.7 has increased quite
I've got slides on that.
Yeah.
This is an old, this is already out of date. Thank you, Robert.
So the 100 is out of date. It's more like 98 now. So yeah, I was sure you would come on to that, but yeah, it's important. Thank you.
Okay. Yeah, sure. So yeah, so the where this 22% comes from is if you take 77 from cloud, so it's 100 minus 25, 77 divided by 340, that gives you 22% reflectivity from clouds. So there's overwhelming evidence of the cloud cooling power. We've had a sudden loss of cooling from the loss of shipping pollution. 100 watts, 1 watt per meter squared along shipping corridors. Actually, Diamond said it could be that there was a range. In fact, that was in the middle. Ship tracks have been lost. They produce from cloud condensation nuclei, aerosol. This is aerosols on which dew forms at the lifted condensation level, dew point. And we rather suspect that the hot waste gases are now not so hot because they're being scrubbed. Not only is the sulfur dioxide being taken out, which was very good for condensation nuclei, but it also cools the waste gases, so they don't lift up so high and form clouds or ship tracks. So here, Earth's energy imbalance. So I've got the red. You should be able to read this easily if you just look at the bold. And the red is the kind of bad news. Earth's energy balance increased up to, Jim has saying 1.36, I believe, at the moment. But of course, these numbers are debated all the time by climate scientists. It took 14 years. So this is NASA. Loeb works for NASA. It took 14 years to double from 0.5 to 1. So we've had a sudden increase in sea surface temperatures. We know this, okay? And so the main body of this presentation is about these 3 cooling mechanisms of tropospheric cloud condensation nuclei: haze, cloud droplets, and methane removal. So haze is these particles that are just in dry air. They haven't reached up to the lifted condensation level, and they can last around about 10 days. It can be weeks, depending on what height they are, how dry the air is that they're in, whether it rises up, to form cloud droplets. Then cloud droplets, which tend to rain out within about 3 days. So also known as you see this called the direct effect, and then this is the indirect effect because the aerosol has made a cloud droplet, which is much more reflective. And then methane removal. And so that's a lot of this presentation is about oxidative radical chemistry. The OH and Cl radicals, these are written like this with a little dot in front of them. Maybe I'll say something about that in a moment.
But Clive,
Yeah.
could the haze and the cloud effect also be the reverse? They could be warming as well. I don't know if you probably cover this later in the paper, but
Yeah, actually, black carbon aerosol has a warming effect. And if you're not careful with cloud condensation nuclei, it can actually clear clouds. So the clouds that would have been there, that would have been doing some cooling, if they're gone, they're not cooling anymore. So you have a net warming effect. So I wasn't really going to say too much more than that, Ron, but we can discuss that at the end.
Well, if I could say, it also depends on what the surface albedo is underneath. So if you put haze over dark ocean, yeah, it'll be brighter. But if you put haze over snow cover or something, it'll be darker. So
Yep. Fair enough.
you do have to
Yep.
worry. You do have to worry about surface albedo, and doing something over the ocean where the albedo is so dark can be very helpful.
Yeah. Yeah. Thanks, Mike. Thanks. Okay. Now, this slide gives us, I've put this together really with lay people in mind. So I know that there's so much depth in all these slides, so much each one we could probably spend 20 minutes discussing. I rather fear that people don't understand. It took me a while, actually. I worked it out for myself. These, but it's obvious to anybody that once you've understood what this is all about. So this is from the IPCC. It's actually from Forster in 2023. So the figures are up to date to 2022. And I look at this as potentials for where could cooling come from with aerosols. So this is now what this slide shows is the change of and forcing means influence, so a heating influence. So we've already seen these watts per meter squared, and this is showing 2.25 watts per meter squared from the additional carbon dioxide that's in the atmosphere. There was already, 280 parts per million. There was already a lot in the atmosphere. Well, whatever it was, at pre-industrial times, and it's increased by about, 50%. And here we have methane, nitrous oxide, and halogenated gases. There's a whole lot of stuff. So, of course, in the media, all we ever hear about is carbon dioxide, and this is one of the most difficult ones to remove. These tend to be called short-lived gases. They can be oxidized. So this is what a lot of this presentation is about, is that the atmosphere's oxidative capacity to remove these short-lived gases. There's tropospheric ozone. There's a certain amount of ozone in the troposphere. Of course, we know it's in the stratosphere, but there's some in the troposphere as well. And here, aerosol cloud, aerosol radiation. I look at those as, that the cloud forcing and haze. So aerosol just radiation without it being a cloud. With huge error bars here because they don't know really, or I think they're getting a better idea now. But at this point, they didn't know. That's the thing that's still pretty uncertain. What the clouds and aerosol cooling effect or the amount was pre-industrially, because there wasn't anybody making these measurements in 1750. And so what the difference is now. So there's a big error bar there. So this is the net of all of those. This just a little bit less than 3 watts per meter squared of radiative forcing, and possibly a little bit of change in the solar. People say, oh, and it's all the sun, but obviously it's just small. Now, what I've done is I've taken those figures and put them into a charting program. And what I've done is I've colored the warming influences that can be oxidized, that are oxidized, the short-lived warming forcings. Okay, so there's methane, that's meant to be tropospheric ozone, there's the organic halogens, these are the main ones. And these are bright red. The kind of pastel colors are unaffected by these aerosols, by the proposed aerosols. And then once again, the bright blue could be increased. So this is the haze forcing and cloud forcing. And this is a chart showing the exact figures copied from the previous chart from the IPCC. And so we see that figure that's just a little bit less than 3 is 2.9 watts per meter squared. This is the heating coming into the Earth. Okay, that's bigger than pre-industrial. Now, we hear a lot about the energy imbalance, but that's not as much. That's not as much. The reason is because the Earth has warmed since pre-industrial times, and that energy budget that showed heat getting lost, it's not exactly glowing red, but I think of it glowing infrared. So it's losing heat, losing a heat at a higher rate than it was before. But we've still got even more coming in. So this energy imbalance is now, this was 2022, so I think we could consider the energy balance more like about 1-ish, plus or minus uncertainty. It's gone up more now because this haze, with the loss of ship tracks, we can assume that these blues have gone a bit less, plus methane's a bit more, especially during COVID, it increased. Reasons I'll go in a moment. Okay, so this is showing, to give you an understanding for those people that are not familiar with these concepts, what might be possible. So clicking some buttons on this charting system to increase the oxidative effect by 10%, these red warming influences have reduced by 10%. And I've also increased the haze forcing up to -1 watts per square meter. So it's a cooling of 1 watt per meter squared, and clouds by 0.8. So this waterfall chart, so what it adds up to and then subtracts back down to now is a radiative forcing, which is about the same as, I didn't know what to call this, I called it emissivity, the sort of glowing infrared. So which would mean that it would stop the warming, but not the ice melt. Again, we can discuss that if someone thinks that's wrong. Brian, do you need to have do you have a question now? Can we deal with it at the end?
Oh, we can probably deal with it at the end. I think the methane number is way too small, but I think it doesn't change your argument about the blue squares. So please continue.
Okay. All right. Thank you. Okay. And then the next, so not the ice melt. So the oceans have warmed, the ice is melting. It'll take a very long time to catch up. We'd prefer not to have sea levels rising. So the next slide is, well, what about restoring pre-industrial temperatures? If the oxidative effect was increased to 50%, these bright reds are half what they were. So we've halved the increase in methane is now halved. So it's still more methane than pre-industrially, but only half what it was, half as much extra what it was. And then the haze forcing. So I can click. I mean, I play with this things sometimes. You could click around and it changes things, right? So doing that reduces the radiative forcing down to a little bit less than even pre-industrial, and which would mean we'd now have a negative energy imbalance, so the oceans would begin to cool down. Obviously, it takes decades for them to change in temperature, but there'd be a cooling influence, and eventually, well, people could argue, well, the ice is not going to stop melting because West Antarctic passed its point of no return in 2014, and people think that Greenland's passed its point of no return, so they're not going to recover ever. But I don't know, I'm not an expert on that. Right, so people get very worried when they hear about proposals to add aerosols into the air. So there's some slides on that now. So pollution gets removed naturally by processes that happen naturally in the air and have been for billions of years. So how the OH radical, mentioned on an earlier slide, this is produced, got a slide later on saying where it comes from. This oxidizes methane. So you could look at an OH radical as it's almost a water molecule. It's just missing a hydrogen atom. This little dot, by the way, means an unpaired electron. So in chemistry, electrons like to go around in pairs. So if you've got a single one, this is probably quite a reactive little piece of chemical. So it's called a chemical species. So the OH radical is looking for a hydrogen atom. And with methane there, it basically grabs one of the hydrogens, and then it's happy, so it's very stable. It's made a water molecule, but what's left behind is a CH3 methyl radical, and that's unstable. So I think I had a slide earlier saying methane is very, did I have that before? Never mind. Methane is a rather inert molecule, plays hard to get. It's really quite difficult to remove it. Maybe it's the next one. There it is. Methane molecule is rather inert. I'll come back in a moment to that reaction. Relative to other, so it's considered a volatile organic compound of VOC. Some of these other ones disappear more quickly and more easily. We know that methane burns fast in a flame, obviously a gas stove, but it kind of burns, in quotes, very slowly at low temperature. We know it lasts about kind of 10 years in the atmosphere. Its removal rate depends on the oxidative capacity, and the AOC is provided by these radicals. So let's come back to this reaction. So once it's lost a hydrogen atom, the methyl radical is unstable, it quickly goes away. So kind of job done, really. As soon as you've moved a hydrogen atom, the rest takes care of itself. So the atmospheric oxidative capacity and the water cycle naturally clean the air of pollutants. So this is not a thing to be afraid of. This is what's been going on for billions of years. So all kinds of gases get removed. That's carbon monoxide. You might wonder what happens to all those cars producing all that carbon monoxide. It gets oxidized to CO2. Okay, and lots of other things here. And also aerosols are removed. All that smoke that goes in the air, we just forget about it. Well, that gets oxidized, gets aged, it becomes hygroscopic, it starts to make better cloud condensation nuclei, ends up getting rained out. Okay, and it's a very big subject, atmospheric chemistry. This is really just top level introduction to those parts that are interesting to us for methane removal. So sources of OH radicals have been long known. We better keep going with this because we're running out of time. Driven by the sunshine. So, for example, it's long been known that ozone plus a photon releases well, an oxygen atom on its own. Oxygen usually goes around in pairs, and then with water we get OH radicals. So, okay, this has long been thought to remove most methane. Also, hydrogen peroxide plus a photon makes 2 OH radicals. And it's also been known for a long time that clouds produce bursts of OH radicals by Fenton reactions involving iron in mineral dust. Okay, weren't really saying where those radicals came from, but this is new knowledge in only the last few years. And here's a plot of an experiment done by this group and several other groups actually, showing the production rate in moles per second of OH radicals compared to the size of the droplets, water droplets. So we see here kind of about 200 nanometers and about 100 times more rate, 100 times higher rate of OH radicals than if the droplet diameter is more like about 300 3 microns, that is there, isn't it? So that 3 microns. So we get 100 times more. Okay, and it produces hydrogen peroxide as well. And they actually observed methane getting removed. They did an experiment putting methane, and it's just getting removed by water droplets. That's it. Water droplets, very tiny droplets. And Franz has a hypothesis as to exactly what's going on, or a lot of detail in any case, what's going on in the droplet to produce this hydrogen peroxide, which is very useful because it splits in sunshine to make OH radicals. Now, natural methane removal is mostly slow. As I said, it's rather inert. I've said all this. But chlorine radical removes methane at least 32 times faster than the OH radical. And the chlorine radical is mainly available near coastlines, volcanoes, and from pollutions. Don't really get very much over the ocean, and even it's hardly any over the continents because there is not a source of chloride. But so why is that interesting for us? Well, methane is removed with chlorine cycling. So fast methane removal, much faster methane removal, given that chlorine radicals removes methane or 32 times faster than OH, If we have abundant OH with some chloride, it's going to be slightly acidic, we can have a low concentration of HCl. So chloride in the form of HCl, which is a molecule that lives in the air. It's also gets into the water. It makes hydrochloric acid. But it's in the atmosphere, it's very naturally low concentration. So Cl gets recycled as HCl. Can you see? Oh no, this has moved. That's a shame. That's that. I wonder if it doesn't. I wonder if it goes away. Oh no. Anyway, never mind. That for some reason that's moved. This is meant to show HCl going around. I wonder if I can just quickly fix that here and unlock that and just move that up there because that's showing HCl. There we go. And lock that there. So if we have lots of OH, then it makes a chlorine atom. Each OH will make a chlorine atom. So once again, the OH grabs the hydrogen, this time from the HCl. So it's happy with its water and it's left a chlorine atom. Now we have a chlorine atom that removes methane 32 times faster. So it manages to grab its own H back from methane, once again leaving the methyl radical to just decay very, very quickly, but reproducing HCl, which can then be used again for the next reaction. So as long as we've got lots of OH radicals to drive this, then the chlorine makes it go faster. It's like oiling the works in a way. Okay, so where does airborne HCl come from? Well, the coastline air contains, the smell of the sea, which is a lot of that's biogenic dimethyl sulfide. It comes from phytoplankton and shellfish. That oxidizes to form sulfur dioxide and then H2SO4, which is sulfuric acid, and sulfuric acid basically reacts with sodium chloride in sea spray. And sulfate is highly reactive, and that would prefer to have sodium, the Na. So that grabs the sodium, and then that leaves behind chlorine and H2, which react to produce HCl. So that's why we have a little bit more HCl in the air in coastlines. Okay. So what are we proposing? So we've got two slides on what we're proposing. What we propose for cooling, we very much like the idea of marine cloud brightening because, as we can see, it has a lot of cooling potential, a lot of cooling power. As we know, as Stephen Salter used to say, it can be targeted to specific areas and it can be switched off quickly if necessary. But we're adding the fact, and we told Stephen this before, unfortunately he passed away, that small cloud droplets are a source of OH radicals, which of course remove methane. So we're also proposing boosting the methane removal further by adding really trace amounts of these compounds. HCl, I've moved this other material to additional slides, NOx and iron 3 chloride, ISO that Franz was talking about, really small amounts. So 10 to 100 parts per billion. So methane is 2 parts per million in the air. So this is what, 20, at most 20 times as much, maybe, 20 times less HCl than the amount of methane in the air. But we don't know. We'd need to do experiments to find out how well that works. What we propose for cloud condensation nuclei, well, once again, it's hard to tell what the size needs to be, but one paper anyway said they measured it from supersaturation levels. They said it's high supersaturation levels detected in the air, which means that the particles getting nucleated must be really small, down as small as 25 nanometers. But anyway, as engineers, we're thinking, something that provides a CCN needs to be able to, provide the size to order, so if we've got air that's full of smoke particles from forest fires, then the particle size might need to be bigger. In any case, it's taken a very long time to there doesn't seem to be really a satisfactory solution for producing salt particles of the right size, at least not without using a lot of energy. So we're suggesting alternatives. Maybe there need to be interim. Here's one, ammonium chloride, which is easy to make from gases diluted in the air. In fact, let's go to this slide, but you can actually see an animation. Oh, what's happened to my animation? I think it's here. If I go back here, there we go. that one there, that's ammonium chloride particles getting produced by mixing HCl with ammonia. So we wouldn't propose doing this in the open air like this. It could be done in a machine, and the machine produces the smoke output. So people, again, get very worried by the idea of releasing, come back to this. People get worried about the idea of releasing ammonia and hydrogen chloride. So, you know, but it's like sodium and chlorine, you know, it's that they are, you know, reactive, nasty chemicals, but when you put them together, they make sodium chloride. We put it on our dinner, don't we? Put it on our food. So ammonium chloride is actually it's also a food additive, so it's non-toxic. Okay, and sodium chloride, but there could be advantages for sodium chloride, so we're not rejecting that. We think it could be vaporized, very hot. Actually, you know, sodium chloride melts around about 600 degrees, and then vaporizes around about 1450, I think it is, degrees centigrade. So by vaporizing, so here's another picture. Here's a picture of a schematic that I drew the other day. Just thinking it was really a very simple mechanism to grind salt. Yeah, so it's still fairly coarse. It's nothing like nanometers. But blow it up a pipe and then have a plasma arc furnace. This is little sparks here, like lightning. These are used a lot in industry. So actually vaporize, needs to get hot enough to vaporize the salt. And then, of course, that quickly condenses in the relatively cold air. But it also produces NOx. We're also thinking add a little bit of iron. Okay. Low energy, because you're not vaporizing water. You don't have to heat up any water. Okay. And yeah, so NOx is handy because it reacts with salts to make sodium nitrate and produces HCl. And actually nitrate is photosensitive, so it's another source of OH radicals. Okay, platforms. Where would this go? Shipping. We think shipping. So we've talked about benign aerosols in shipping. So actually the waste gases and the waste heat are useful for both marine cloud brightening and methane removal. I just thought I'd throw this in. Franz for a long time has been suggesting whitening the smoke particles. Given that black carbon aerosol warms, I didn't realize it was quite so much until I was preparing for this presentation. I found as high as 5.53 watts per meter squared. That's enormous. That's about the same as methane. Okay, so this just turning it white in shipping. Right, I think some of it's scrubbed out at the moment. So this is another, really, to me, another area of that should be research and development to see if the black smoke could be removed. Anyway, so talking about platforms, shipping. Ships don't always go where you want them to go, and the oceans are, as we know, absolutely vast, 70% of the Earth's surface. So buoys, tethered. Trouble is, buoys, most of the ocean is very deep, 4 kilometers. That's rather expensive to tether them, but there's, you know, continental margins, continental seas, shelves that are much shallower, and some of them stretch quite a long way out to sea. Goyos is seamounts that are quite near the surface. So, you know, and so on, possibly even land-based, can make some thermals. Thermals can create clouds. Locations, we suggest tropical ocean. This really is down to meteorologists, not so much us, but we think that from what we know, you get a bigger cooling effect. The Earth gains heat at the equator and it loses it, sends it out to the poles and tends to lose more heat from the poles, or it does lose more heat from the poles. So there's a lot of heat coming in at low latitudes. We could produce that. But it's also good for your equipment if you want to power your equipment from the sun. Windy coastlines, hot remote deserts, and so on. Where are we now? Well, we think we've got some compelling questions. We need and actually spoke to some people only Tuesday night. Gentleman that we know, Vic Garney's, was saying actually his laboratories are able to measure very small quantities accurately and simulate the outdoors with sunshine. And we'd like to apply for funding from ARIA, the UK Advanced Research and Innovation Agency. We've also been speaking to Ocean Cooling Technologies, part of the Lothian School of Engineering set up by Stephen Salter, and also the Blue Cooling Initiative. We know we've been speaking to those people as well. They're interested, and we're very glad to help them as well, provide whatever information they want from us. So what's needed? I mean, the thing is that Franz is in his late 70s. He's still going strong, but he's in his late 70s. And I'm volunteering part-time. I have to make a living in other ways. We've patented our proposals, or in the process of still patenting things. More funding is needed to secure our IP. We're open to offers. Basically, we need a bigger team. So please contact me if there's anything you think you can help us with, or you'd like to get involved. Links to papers here. We've got much more chemistry in this paper here, and I was asked to put in these links, these great papers that Ron has lead authored. Okay, that's it. Thanks everyone for listening. Questions, please.
Great, thank you.
Comments.
Thank you, Clive. Yes, if people could just raise their hands, and we'll try and go in order. If somebody can just keep track, I think that the hands up will work. That will keep track of things. So I see Brian has his hand up. So Brian.
Yes, thank you, Clive. That was very interesting. Minor quibble on the red and blue boxes, and that is that if I just do a rough calculation on the methane, what we're really looking at is 2,000 parts per billion. And, you showed a chart for 2022, and this is not your fault. This is the IPCC's fault. In that year, we had 2,000 parts per billion of methane. And, they like to use the 100-year forcing, which is ridiculous because the level of methane is not going down, it's going up. And so we get, 2022, the instantaneous methane for that year was 120, right? So you take 2 parts per million times 120, you get 240 parts per million CO2 equivalent. And add that on to 420 parts per million for the carbon dioxide, and you realize the methane box has to be at least half as big as the CO2 box, and it's not. And so this is a case of what I would call gross negligence and regulatory capture of the IPCC. So anyway, it needs to be adjusted. I think the story is there. We need probably the marine cloud rebrightening even more because of this. But this is just an example where these little insidious assumptions that the fossil fuel industry is very nicely put in to, embedded into the IPCC cultural memory is just wrong. It's just plain wrong.
Thank you, Brian. I think I did wonder about that some time ago. Looked at it and I thought, why is it so small? Given that, as you say, the instantaneous warming is about 120 times that of CO2. Yeah.
No, we just, in an atmosphere where the CO2, where the methane is level or going up, we need to use an instantaneous number to really talk about what is happening in 2022.
Agreed, absolutely. So that's, in a way, that's very good news because that shows more scope for cooling.
Right.
Definitely. Effect. Yeah, that's great.
And then the other thing I really love the chemistry that you and Franz are working on. I've got a lot of arrows in my back when it comes to social acceptance. And I've watched people, die on their swords when it comes to social acceptance. And I don't, I'm just concerned about the number of decades it'll take to get social acceptance on ammonia and hydrochloric acid being used, on a broad scale. I do appreciate that, sodium chloride is very stable and that's good. But this presents a little golden opportunity, and that is you had some beautiful slides on dimethyl sulfide. And, there's the biogenic production is mostly near the coast today. But what's interesting is that with interventions of marine permaculture, macroalgae and microalgae can apply to the broad areas of the ocean and not just the coastlines. And so this, to me, represents a sea change opportunity, to pun a phrase. and that is
Yeah.
that why not embrace natural processes? In fact, I can make a case for 1/3 hectares of missing kelp forest in the US and Australia alone. And we haven't counted the UK or Europe or Namibia. And so just 2 out of 100 big ocean nations, we can document the need to get 1/3 hectares of kelp forest back. No one alive today has a living memory of the kelp forests that were in the 1800s, but we do have the USGS maps and we do have the other documentation. My proposal is that we could get social acceptance much sooner for the restoring and regenerating the nature-based ecosystem services, which include biogenic aerosol production. As you have so articulately described, this beautiful mechanism of taking natural biogenic aerosols, the wonderful smell of the sea, and that's the dimethyl sulfide, and the sodium chloride that's already there, and just say, look, we're just restoring the level of biogenic aerosols that we had pre-industrially. And now you get your entire mechanism with something that we could build social acceptance for in months or years rather than decades or centuries. Anyway, just a small suggestion. It's a big upside. Happy to discuss this with people more, but that's where we're trying to take, this kind of regenerating ecosystem services that are nature-based biogenic aerosols, and yet you're still getting that mechanism that involves the chloride ion. It just is done through this nice natural mechanism instead of having to be talking about hydrochloric acid.
Sure. Okay. That's great. Thank you very much, Brian.
Pleasure.
Brilliant.
Thank you, Brian. Mike, you're next, I think.
I want to go first back to what Brian was saying about GWP, because it really isn't appropriate to be blaming industry. That's not what happened. Guy in my group at Livermore came up with the concept. So realize it came from stratospheric ozone. There were thousands of different ones. Negotiators can't even consider, they have trouble considering one, much less 2 different things. And so it was a way of combining, and then they did it for the positive forces as well, and realized that when that started, chlorofluorocarbons were one of the really positive influences. We're going to be a warming influence, and there were a lot of those things. And so that's where the GWP started, and they sort of, did 20, 50, 20, 100, and 500 years. And if you give them 3, they choose the middle. You're exactly right, though, that it hides the important ability to try and go after methane. So okay. I'm just going back on your history a little bit, but I agree with you. And a number of us have been doing it. In fact, it was what caused the kind of strong difference in the 1990s between what Jim Hansen was saying at one point and what John Holdren was saying when he was science advisor. If you look at the IPCC charts for forcing in 2000 and 2100, you will see that the biggest change is in CO2. Okay, the forcing goes up a lot. And so John Holdren said, well, that's the one you have to go after. And so that became the focus on CO2. Mm-hmm. However, if you think about the charts and you want to go after emissions, and all we can go after is emissions in the 21st century, because we were at 2000 or something, all of the methane excess, because it has a 10-year lifetime, has come out in the last 10 years with, it's a little longer than that, but so the full amount of methane in the 2100 chart, you can go after, or something like that. The full amount of black carbon, the full amount of tropospheric ozone. You can't go after the full amount of CO2 without a lot of work, but you can go after. And so the short-lived ones, there is this push to go after short-lived species because you can do something, and it's really important to know. I will go back and say, Clive, that I don't think N2O counts as a short-lived species, but no. I think there was a recent seminar given with U.S. and some other U.S. and China, I guess, which are major sources of N2O, saying that there are all kinds of ways to change industrial practices to reduce that, and that they're trying to do that. So they are doing it. The question I have for you, Clive, is given the ocean is so big, and so methane is coming up all over the ocean, it's above the ocean everywhere, and so presumably is hydroxyl. Why is there any methane in the atmosphere at all, given that the ocean is so big? And how is incrementing going after the methane, in some small coastal area or in some areas, going to really get at the methane concentration if so much persists, even though the ocean is doing so much, must be doing so much already. It's so large. It must be putting up so much chlorine.
But the ocean isn't producing much chlorine atoms because most of the dimethyl sulfide comes from coastlines. Most phytoplankton, the most productive parts of the ocean are the coastlines, where the seas are shallow and they're close to the sediments.
So it's a perimeter effect that needs to become an area effect, and that's the challenge.
So that's what Brian was saying. It's just the coastal stuff is generating the chlorine part.
Well,
yeah.
we don't know. This is what we suggest. This is what we're hypothesizing. That most of the ocean is mostly just OH radicals. There's not really a lot of chloride. There's some, but not much.
You've actually raised on a critical thing, Clive, and that is that we've seen decreases in primary productivity in subtropical oceans by 30 to 40% over the last 60 years. And that means less dimethyl sulfide production, which means that we may be getting a lot more of the methane than we'd paid for or whatever. And so we're getting even more of a coastal effect now because of the decline in productivity of these subtropical oceans. So if anything, the problem's getting worse because there's less TMS available.
Methane is produced mainly in anaerobic sediments and so on.
And rice paddies.
Yeah, methane doesn't come from the ocean. I don't think that's what you meant.
No.
You're saying
really,
right, but
I mean, there's a huge potential.
But there's so much. Yeah, it would seem there's so much potential for OH and chlorine to come from the ocean that it would be going after the methane.
Yeah, so there's
methane is eaten by microbes in the ocean.
Yeah,
True.
in the ocean itself. Yeah. So there's a little bit of tropospheric ozone all over the ocean, and when there's UV, there's some OH radicals. So that's considered to be, as I understand it, most atmospheric chemists, at least up to now, have thought that most methane is getting removed by OH radicals, which mainly come from ozone splitting from UV in the air all over the world. So the ocean and everywhere. They don't distinguish between ocean and continents. We're saying that given that the chlorine atom removes methane much faster than OH, where you have a little bit of chloride in the air in form of HCl, it's going to be going faster. So methane is getting removed not at the same rate everywhere. So where there's more HCl in the air, and especially where there's more OH as well. So coastal clouds are going to be the ideal places where most methane, where methane is getting removed at a higher rate. We suggest, we don't know, but we suggest, because all the elements are there. There's in small cloud droplets, you've got more OH, a lot more OH getting produced from small cloud droplets. It wasn't really recognized before. And then if there's some HCl available as well, that, as I said, it's like oils the works, because the chlorine cycling can remove methane that much faster. That's what we're saying.
And one more question, just to clarify your chart on OH coming from small particles. Is that per particle, or is that per?
I don't know.
Mass of material when the particles are small?
I kind of have that question myself.
The mechanism is complicating and not totally clear how it is produced.
This one here.
Yeah.
I mean, moles per second. That must be. We have to look at the paper. The paper's referenced. I can send out the PDF.
Usually, it's measured in. Such particles are measured in micrograms per cubic meter. So I think it's normalized to mass of suspended droplets.
Oh, okay.
There are a lot more particles at the small size, which is probably why it works.
Well, you get much more surface area. Yeah, right.
Exactly.
Okay.
Yeah.
Particles,
we also
the smaller they are, the more acidic they are on the outside, and the more basic they are in their interior. And to our knowledge, it happens that oxygen is round about these small droplets, and it is a little bit soluble in the water phase of the droplets, and it may be reduced in the middle where the OH ions are concentrated. Between the middle of the droplets and the outside of the droplets is a difference of is a strong
Electric field, yeah.
Electric field of 10 exponent 7 volts per centimeter. Yeah, and this is also a possible cause of this chemistry of this.
Yeah.
The smaller the droplets, the bigger is the field, the electric field.
Yeah.
And the more H2O2 and the more OH radicals that you have in them, as this diagram has shown.
So as we clean up fossil fuel use, tropospheric ozone goes down, and so the methane stays even longer, I guess. Is that also true?
I would say
lower ozone would
white
be
clouds,
higher methane.
white clouds make more methane depletion than dark clouds. That's a consequence.
There's several things. Yeah.
So
yeah. Go ahead, Ron.
Yeah. Thank you. We had some experts on there, so I wanted to let them sort of go at it. But normally we have one follow-up per question. So, but if people are, this requires a lot of technical knowledge. So if we welcome the internet, additional discussion from the folks who know more about what they're talking about. Robert T.
Look,
Yes, Robert T.
Yeah, thanks so much, Clive and Franz. I think what you presented is really brilliant, and I think Franz is one of the great climate geniuses of the world. His understanding of atmospheric chemistry is really vital, and it's been, I think, a scandal that he hasn't had the recognition. And it gets back to the point that Brian raised about social acceptance, and the fact that we've got this pathological mass psychology of emission reduction alone, which is just completely ignoring the role of albedo in warming the planet. And as James Hansen has recently said, the collapse of albedo just since 2015 has been equivalent to 100 parts per million of CO2, which is an extraordinary problem. And so my view is that presenting the message in a simple way to the general public can rapidly turn around the understanding that if we do address albedo, then it's a lot faster, it's a lot safer, it's a lot cheaper than addressing CO2. I think the safety factor comes in, especially in the tipping points issue, that if we restore planetary albedo, then many of these accelerating feedbacks can be hopefully nipped in the bud, but we really need to do it quickly. And so I think Hansen also commented that marine cloud brightening is the most innocuous way to cool the planet. And what I really liked your slide, Clive, about the arc furnace, this idea that just getting dry salt. Now, I assume that the arc furnace is able to optimize the size of the salt particle. So, a lot of the analysis saying 0.8 of a micron or 0.5 of a micron, whatever, but being able to test the size of microns. And then I think what Franz has really introduced is if we have this marine cloud brightening production, And then if we add other elements into it, you've mentioned iron, and there's also titanium, I believe. And
Yep.
it's the idea that using this arc furnace method, which it seems is an alternative to the Salter method, Stephen Salter's wafer production of marine cloud salt particles, aerosols. So it's just fascinating to see that there are all these different technologies, and then both the method of production and also the composition. Just we would be able to really reduce albedo quite rapidly. So well done on the presentation. I think it's really important. And if there's anything in what I've said just now that you'd like to reflect on further, please go ahead.
Thank you, Robert. Thanks for that. The salt particle mechanism, the arc furnace would naturally produce. I would expect it to be able to alter the size of the particle by varying the speed of the air through the thing. So we think that there should be plenty of scope, and there are companies that make several companies that make nanoparticle generators that use.
Clive, can I tell
please,
that you can do it? You can do it also in a flame, in a hydrogen flame.
Hydrogen and chlorine.
Yes.
Yeah.
And if someone says, "Oh, a bad NOx is a byproduct," you can give a little bit of ammonia, and then you can reduce also the NOx. No problem.
Oh, that's interesting. Would that also apply to N2O?
What's
you
the
last-
N2O?
The nitrous oxide production is interesting, but you're saying if you add ammonia to your flame, would you also reduce the amount of N2O production?
You know, it's known from the diesel cars. They diesel engines, you can reduce NOx by ammonia or things or chemicals which produce ammonia.
Okay,
Yeah,
and that would include
ammonia
N2O as well in the NOx category.
Yeah.
Okay.
It removes N2O as well, Franz, not just the NO2.
Yes,
it removes N2O also.
Yeah,
but most N2O is produced by nature, I think, and not industrial or by burning or so.
Right. So most of the NOx that comes from a high temperature is not N2O. It's mostly NO2 and these kind of N2O.
I thought of N2O.
I think one of the issues, though, is that a lot of this chemistry just goes totally over the heads of most people, and so finding ways to present this information in really simplified way, and ideally get it into op-ed articles in mainstream mass media newspapers. And there's just been no progress on that. So all of this material is completely unknown to the general public, and I think that that's a scandal, which it's really important, firstly for the climate community and then for the general public. But we've got such major barriers for Tim Lenton to be saying that all of this material must be suppressed in order that we can cut emissions, and that will somehow slow tipping points. I think he's crazy, you know. Whereas what Franz is saying is just eminent scientific sense, and it really ought to be up there in a big public debate.
Okay.
Yeah, thank you, Robert. Yeah.
We must produce a paper. First produce a paper, and then it can be discussed.
We're kind of, thank you, Franz. We're getting to. I put my hand up because it was some of the earlier discussion, and I know Mike was a big part of this, where we were trying to respond to the reviewers' comments on your method for the cooling paper, and we were trying to figure out whether you were proposing SRM, the solar reflection radiation what is it, management now, or
It's
yeah, I know, modification management, whatever,
yeah.
or TRM, thermal radiation management, which would more apply to the methane reduction. And
Yep.
which part of the process, and we had some confusing. Originally we thought TRM, because we were talking about the methane removal potential, and methane being a short-term climate driver. If you cut the emissions, you actually get a pretty rapid cooling. It's not like CO2 where you have to cut the stock dramatically to get cooling. So short-term climate drivers, I think it's the term we use. So methane is one of those, and that would be a kind of a way to get cooling by reducing the captured thermal heat from greenhouse gas from methane. So so then you convinced Mike, I believe. I mean, Mike was the person who was really doing the trying to do the expert evaluation of this. And I don't, I think we did finally agree that yes, that the SRM part of your method was the stronger part. You were making that claim. So I'm wondering if you could elaborate just a little bit more. So particularly doing it on ships, which because we're proposing that this could possibly be a alternative to sulfate aerosols from fossil fuels from ships.
Yes.
Whether how so I'm getting a little bit more of the picture that you could use the heating from the engine to possibly produce some of these more active kinds of aerosols or stimulate. So what part of that would actually, and where did you come up with that estimate that the solar radiation, the SRM part of the method would be the much more impactful in terms of cooling? If you could just elaborate on that, I think that would be helpful because it is one of our primary direct climate cooling techniques in the paper.
I think it acts at once,
I'm sorry?
to make making a bright cloud and the shadow of this bright cloud, you notice it at once when you get the shadow. And maybe we are not sure if the methane effect of this process acts at once also.
Yeah, as soon as methane's gone.
That's a question. Which acts faster, the methane effect or the thermal effect or the albedo effect?
Yeah. And the cloud is immediate there. Yeah.
We are so happy that we can discuss this question because we are making both, both effects.
Right. So
I can, if I can, and I think you're asking about the amounts as well, Ron. Which is the greater effect, and I got it from here. But Brian has just said that I thought I should use the IPCC numbers, that this one for methane is 0.56, and that's only 0.56. That's not even the energy imbalance, which is now more than 1.3. This 0.56 here for methane is less than half the energy imbalance. So that's why I was saying it's not very much. But Brian has just said, well, the IPCC is wrong. That should be much more because they're using the 100-year. That should be much higher. They haven't used the instantaneous warming effect of methane. They've just said okay. So that means that I've kind of bit wrong to say that the thermal radiation management, TRM, is too small. It's much smaller because maybe it should be maybe double or triple this amount. But so that there's the aerosols. I think that doesn't change because you read the modeling studies from marine cloud brightening, and they will say 1 or 2 watts per meter squared. Does that answer your question, Ron?
If I can add in for a second, though, Clive, I mean, I'm not sure you can do quite what Brian says. I mean, if what you do is you say, well, I'm going to do all of methane's effect in the next 20 years or 10 years or right when it comes out. So the GWP is based on per pound or kilogram of emission or something like that. So you're sort of using up all your methane one now, if you're going to say at 20 years, and then the emissions 20 years are doing it. And so it's sort of continuous over time. So it's, if the emissions stay constant, it really, I don't think sort of matters too much, because you're just sort of counting different emissions, giving the heating at different times, but you're having the same amount of emissions over time. The key is if you can get emissions coming down sharply, what the methane initiative is going to do, because then it comes out, and then he's right, most of the heating is right at the near term when the emissions are high and goes away over a longer time. But he's sort of right if we're getting emissions down, and hopefully we are. But if they stay the same out to, which is what caused that confusion between Hansen and Hansen and John Holdren, was that they were assuming constant emissions out and not getting rid of stuff. So.
Yeah. Thank you, Mike. And to elaborate on that slightly, there's a very subtle distinction, Clive, between your two charts. The first one was 1750 to 2022. And it's quite possible the net greenhouse gas over that centuries for methane, it may be as small as they show. But then when you go to the second chart that says in 2022, how much warming do we have? Well, that bar has to be a lot bigger for methane, because that's what's happening in 2022. And so that's the distinction, is the time frame.
But that's meant to be the same. This is the picture in 2022. Can you see this?
Well, it's 1750 to 2022. So that means, okay, averaged over that time, maybe methane was a big deal. But now you go to the second slide, a very subtle timeline shift. And your second slide after this one is just 2022. And that's, well, in 2022, it's having this much effect this year.
Right, but no, these bars are not showing the average between 1750 and 2022. They're showing the change since 1750.
Oh, all right.
Yeah,
well, then it could be
the accumulated change. Yeah, right.
Well, so if it is just a 2022 change over 1750, then probably the methane bar needs to be larger as well.
Yeah, I mean, yeah, you've said that before, and I agree with you. I mean,
it's all about timeline, and I think we need to be looking at annual timelines at this point.
Right. What to do is not be using GWP. That's the main thing.
We got to use what is it? What's happening this year?
What's happening?
There's two useful ways to think about methane in the air. One is, and with carbon dioxide, economists think, well, what's the damage done by releasing this amount of gas into the air? What's that? That ton of methane, what happens to it? And they say, well, it decays, and so therefore we sort of integrate that, and this is the amount. So that's a useful measure to think about. Well, how much methane does it cost? What should we do? Should we stop it or what? Then the other, but from my point of view, we're thinking about the amount of cooling going on, or the amount of heating from methane that's there right now, is to think about the instantaneous effect right now, because as you say, some of it goes away, but some more comes back from another swamp, or another gas well. Or what worries me is with these rapidly rising, not just me, sea surface temperatures, if you've got warm water flowing into the shallow Arctic seas, people like Natalia Shakova saying there's a huge amount of frozen methane under those shallow seas, and we could get a massive methane burst.
They won't stay frozen for long. We know that much.
Yeah.
So I'm gonna, I've just been reminded.
Sorry, Ron, you've got your hands up. I don't know if it was me that was supposed to be managing this, but there's lots of hands up. So
I know.
I wasn't sure if you were doing that.
I'm sort of. So thank you for that. So Jonathan Cole.
Thanks. Great presentation. I wanted to zoom out a little bit away from the nuts and bolts of methane. You talked about, or I think it was Robbie talked about, how presenting this information is quite difficult. It's coming out of left field, so to speak, for a lot of the audiences that see it. I had a similar problem in a presentation creation for someone who wanted to talk about cirrus cloud thinning. And let me show you what we ended up with. We tried going directly at the science, and nobody understood what we were talking about, except for people with PhDs in similar fields. And so we ended up having to get really basic, and I'll show you what we came up with. So we had to start from the idea of what does an atmosphere do to a planet? And you're welcome to these slides. They never got used in the presentation. The person left the movement before they gave their presentation. But anyway, we had to show the idea that the reason the Earth is livable is because the nighttime temperatures are actually modified by the warming effect of the atmosphere and the clouds. That planets that have no atmosphere get super cold on the dark side, and that's not very good for life. And then, of course, very cloudy planets like Venus become very hot on the surface because of enormous effects. So we had to start from there with a little explanation. And then it turned out that most of our audiences understood that the cloud cover over their city kept their city warm at night. So we had to admit to them that all types of clouds, even the ones we wanted to deal with, create warming effects at night, because they sort of understood that, they could identify with that. And then we had to point out that certain types of clouds during the day also had a warming effect because of the way they were structured. And that we were only interested in creating one type of cloud, which was the bright, shiny white ones. And, we went over the ship tracks. But then we started to get into the science for the cirrus cloud thinning, of the energy bars and stuff like that. But we didn't bother using the big energy forcing imagery, with the big bars, because there was so many numbers on that one. And we just kept, going with this stuff. But anyway, I just wanted to show you that, and you're welcome to, any of those slides. But
all right,
starting at the basic idea of why does a planet need an atmosphere? What's the ideal atmosphere? The effect of what you're doing is going to have one effect at night and one effect during the day, and how that works out to equal what you want, which will be cooling, I suppose.
Yeah. All right, thank you. I mean, this audience is not. I consider this audience people who are very interested to know what might be possible to provide cooling, and are willing to learn a little bit of science. That's not your average man in the street. So, it's different audience needs a different kind of thing. Yeah. Yes. Okay. Yeah. Thank you. Okay. That's happy to look at anything, John. Yeah. Send me the slides, please. Yeah.
What I wanted to say to Jonathan, when you're in a desert, which is very hot during day, and you have clear heaven, and in the night the temperature goes very down. It's totally right what you're saying.
Yeah, I think you could also say, John, that it's low-lying clouds that provide an overall cooling effect.
Only day, during day.
In the day, and they all clouds keep us warm at night, but during the day, the low-lying clouds, they all reflect sunshine away, but the low-lying clouds are warmer, and so they're glowing more infrared out to space, whereas really cold cirrus clouds, they're not really emitting much infrared. That's how I understand the main reason why low-lying clouds provide an overall cooling effect, whereas high-altitude clouds don't. Rebecca.
Yeah, Rebecca.
Hello, Clive, and everyone. Yeah. It's so lovely to hear your general presentation, even though I've had the privilege of reading your two-pager and commenting on it.
Thank you.
I'd like to frame Robbie's comments about strategy, I have got a question as well in a moment, which is related to my framing, but this audience here is very familiar with history of science, history of thought, and that kind of thing. In terms of Robbie's comments on media strategy, what is needed, I agree with him, is a clear presentation in the media of the debates. What are the scientists arguing about? What do they agree on? What do they not agree on? The rock solid things like what John just presented then. Why do we need an atmosphere? What is an atmosphere? What effect do clouds have? And the distinction between those is kind of primary school intuitive knowledge, and then knowledge like myself, who actually did university level science and late high school physics and chemistry, that kind of thing. So people like me that are educated, I like to see the graphs that you've presented, because what they are showing me is what is rock solid and agreed on, and what are the debates, and is it about data, the sort of thing that Brian was mentioning, percentage in the atmosphere, and even then, what are the implications in this rather more deeply diving audience? What are the implications of those data differences? But I do agree with what I'm sure we all do, that this stuff needs to be presented to the general public in the daily pages on the 7:30 report. That's one of our commentary shows in Australia. My question is about the implications of different names, and the one that you've chosen today is natural tropospheric aerosol processes. Another one was climate catalyst aerosols, and the one that is in the papers that are in pre-publication stage is tropospheric aerosol injection. So what I'm doing here is really giving you a chance to reflect on those names in terms of mobilising individual actions, and also political action about regulating fossil fuel companies and other legislative and regulatory changes. And really in terms of the implication for people's emotions, whether it's going to get people to do something, to block something, that kind of thing. Of course, there's always divisions, like here in Australia, we're 50-50, red and green or left and right kind of thing, and we swing between the two, with a bit of a fringe radical left and a bit of a fringe radical right as well, which of course you can tell that I'm not very fond of those people, even though I like them as humans. But so my question is, what do you think the implications are of those different names for micro and macro political action, putting aside practical questions, which is a steering circle discussion about where is the papers up to in publication, that kind of thing. But what would be your preference and why for the name of your method, of you and Franz?
Well, I changed it to natural tropospheric aerosol processes as a general name that's got the word natural in it at the beginning. It says tropospheric, you know. I agree that, you know, a name needs to be important, but very few people know anything about, you know, I didn't know much about atmospheric chemistry, so how can you expect people to know? We do our best. Yeah, Franz.
I would say injection is a bad name. I don't like injections in my body, and nobody. So I would like the name you choose, Clive.
Yeah. Okay. Thank you. Yeah. I mean, we chose it
because we should do
show,
like.
Unfortunately, that climate is close to last in importance for young voters.
It's last in
Sorry,
importance
Herb,
for young voters.
Herb, hello, woo-hoo. I didn't hear what Herb said, because
yeah, well, I don't know if Herb, were you trying to
lose
can you raise
many
your
more
hand,
votes.
Herb, can you raise your
If
hand
she
and then we can
is
get you in the
seen
queue?
as
Ron, Herb, we
I think
cannot
his-
hear you. People are
Yeah, I
speaking.
think his mute. Let
Herb,
me see if I can fix that. I gotta go to gallery and go to Herb, and I use my special powers. If I can find
as
him.
you are.
Oh, there we go. I got it. Okay. Dang.
Robbie, are you able to mute Herb? He seems to be on a phone.
Oh yeah, it's got to be Robert. That's right. I don't have special powers. It's the host.
Okay, thanks. Sorry, Clive and Franz. Back to you.
Okay.
what were we saying? You were saying something, Franz? Yeah, Franz said don't like the word injection. I think they wanted a different name, and I don't know, we're always busy, so that seemed okay because it would distinguish it from stratospheric aerosol injection, which so we wanted to be distinct from that, and they often get conflated. It's all just solar, radius SRM. It's all just the same thing. It's aerosols. That'll do. People don't know that there's a stratosphere and a troposphere. So, and it's very different. The processes are very different. So, but as you say, injection. Now that on reflection, we don't like the word injection. So, I mean, I think people tend to agree that on that. We can't. It's very difficult to change it in the paper, as we know. We've seen all those emails going back and forth. So,
well,
if we
Clive,
get the chance, we should just say to people,
that's a steering circle question, and we're having a meeting after this, so I don't think you need to engage in that one.
No, all right, then. Okay. But so for me, if anyone comes up to me and says, tell me about tropospheric aerosol injection, I'll say, actually, we want to call it natural tropospheric aerosol processes. That's what we call it nowadays. That's its name, NTAP, not TAI, but NTAP. I'll just say that to them and then move on quickly to answering their questions.
Yeah, and we're very happy to offer rebrightening as our platform for rebrightening the planet. I mean, initially, we think it needs to be community-led and local and regional. But effectively, one of the reasons we're developing the rebrightening platform is to begin this reframing process to where communities can really help co-design and lead, taking action to actually ensure that their locales and their regions are going to have a healthy climate in the future, despite what the world may do. And we'll start at a small scale with a high degree of social acceptance. So very happy to, embrace multiple approaches. We need to create a menu of how of all the items that communities can choose to rebrighten their locales and their regions. And thankfully, communities can choose one region at a time to begin adopting the new approach. And hopefully this will be like Buckminster Fuller, inventing something new that will make the old framing obsolete. So that's our aim.
Mm-hmm.
We're almost out of time here. I just want to know if anybody has any last questions or comments. If not, I will turn it over to Clive and Franz for last comments. I do want to just note that we can leave that for other forums, but yeah, Clive or Franz, thank you very much for your presentation. It's been really informative. Do you or anyone else have any last comments for Clive or Franz? Go ahead, Brian.
Yeah,
that's just applause. I want to say big thank you to Franz and Clive for this great work, and look forward to collaborating on this in the future. So that's just applause.
That's great. Okay, thank you very much.
Great,
Brian.
Great. Yeah. And obviously, Clive and Franz can any of us who was interested in this and wants to help out could obviously contact Clive or Franz to see how to help with this. Clive or Franz, you want to last words?
Thanks for having us. And
okay,
I couldn't have done it without Franz. I mean, Franz is an amazing. Sorry, Franz.
Questions.
Yeah.
Only wanted to say thank you for the kind question.
Mm-hmm.
Thank you.
And we are going on to look to nature if we learn something new.
Yeah. Okay. Well, thank you very much for doing this, and we look forward to this, becoming an important direct climate cooling method. So I think we all agree on that. So, so goodbye, everyone. And,
great stuff. Thank you, Ron.
Yes. Bye-bye.